My name is Mikko Tiili, and I'm here to present my thesis on the potential of district heat electric boilers in frequency-controlled electricity reserve markets. And the motivation for this topic comes from the important role of district heating in colder climates such as Finland, and its connection to the electricity production. It used to be that much of district heating was produced by combined heat and power plants, and they were an important part in the electricity production in Finland. But now, as we are moving away from those and changing to electric heating systems, there is less producers and more consumers on the district heating part, and then this means that there is no more that much of the stable electricity production, and now it's more flexible, and then at the same time variable renewable energy sources such as wind are taking a large part in the electricity production, which means that we need more flexibility on when to consume the electricity. For example, when it's not that windy, the prices are high, and there is need to reduce consumption of electricity. And for my research questions, number one is what are the optimal reserve markets for these boilers to take part in, and this is from the technical point of view. So what are the possible change speeds and ramp speeds, and what is technically possible to accomplish within the district heating network. And then the second one is how does the connection to the heating system affect the capability of adjustment, and this is due to the electric boilers being able to have greater ramp speeds or change their power very quickly, but the problem is with the hot water, and you don't want too much change in the water temperature. And then the third one is what are the optimal reserve markets from an economic view. So what would make the most sense in making district heating more competitive and make it more sustainable in the long run. Then quickly about the scope and limitations of this thesis. First of all, it only focuses on one plant that I used as a base, and so it might not be universally applicable in every situation. And the case study is also based on an unfinished plant, so there has to be a lot of assumptions made, and there are some things that are not yet known or parts that are not ordered, so it is hard to know exactly what are the capabilities. And then quickly a little bit of the heating basics of district heating. So district heating is based on centralized heat production. So you have one large heating plant, and then the heat is supplied to consumers through large pipelines that are insulated. And this district heating is especially effective and efficient in densely populated areas because you don't have such long distances and not that much pipe to build. And then it's also you get less heat dissipation through the pipes. And so in rural areas it is much more expensive to build the long pipelines, and then you lose a lot of heat in the process. And electrification of district heating. So Electric boilers, heat pumps, and heat accumulators have made a big difference in the later years, the few years after like 2020. And 1976 is the beginning of this graph, where you can see that coal and oil is the main way to produce district heating, and then it's been going down pretty steadily, and now we soon don't have any coal plants operating, and then biomass has also taken a large chunk. But the heat recovery and electricity is very rapidly increasing, and in the few future years it's going to be a very substantial amount of district heating production. And electrification, as I mentioned before, adds more consumers of electricity, but less producers. And this is part of the problem that we need to tackle. And here you can also just see the CO2 emissions of district heating has been going down very fast, and it is one of the reasons why it is very good way to heat, as it will soon be very minimal CO2 emission way of producing heat. And then the main focus of this thesis is the electric boilers. As I mentioned before, there are also heat pumps, but they are not really that good at altering their power, so it is out of the scope of this thesis. And then there are many different kind of boilers, but I'm focusing on the electrode boilers because they have fast ramp-up speeds and very high efficiency, compared to like resistor boilers, which are usually used in lower or smaller applications due to the slower rate of heat transfer to the heated medium, whereas in electrode boilers the electricity goes through the water and conducted through the water, and then the water itself heats up through the resistance. And these are very good because of the fast ramp-up speeds, and it is good for the electricity grid balancing. And then a little note that the heat accumulators are very key in this, in the boilers participating in the markets, as the need for heat is constant, and there's a certain temperature of water you need to supply, and then it can't really vary that much, and big variations can also lead to problems in the network, such as pipes bursting. So we don't want that. And then a little bit about the reserve market. So now that we have more wind and solar, there's less grid stability and need for fast flexibility. So basically we just want to have these different components in the grid that can then flex according to the needs of the grid. Let's say it's not that windy someday, and then we need to have something to either produce more electricity or reduce the consumption. And the flexibility of the electric boilers is very good for this. And then the overview of reserve markets. So here we have the fastest one is the fast frequency reserve, which is mainly for low inertia situations where HVDC link or a power plant fails, and then we're trying to keep the grid over 49 Hertz, and 50 Hertz is the normal operating, so we don't want it to go over 1 Hertz deviation. The next one is the FCRN, which is the frequency containment reserve normal operation, and this is for deviations from 50 to 50.1 or 49.9. So it's 0.1 hertz difference when this is activated, and it's activated linearly. So at 50 it's 0, and then at 50.1 it's full activation, and it's linearly through that range, and it's continuously operating, and it's also symmetrical, so it goes up and down. And then we have the FCRD, which is for disturbances, which is from 0.1 deviation to 0.5 hertz, and this is sort of for higher deviation, so it's a little bit faster reserve, but it's same way, it's linear in that frequency range. And then the last one is the automatic frequency restoration reserve and manual, and this is sort of out of the scope of this thesis, because we know that as we can see, the activation times are in like 15 minutes, or then in the automatic is 30 seconds, and 5 minutes to 100%, which is plenty of time. So we know that we can take part in these reserves, and we are mainly concentrating on the FCRD and the FCRN, because the FFR minimum bit is 1 megawatt, activation is 1.3 to 0.7 seconds, which would mean a ramp speed of 86 megawatts per minute, and that is way too fast for district heating. And in this thesis later, the case study, it's the electric boiler is limited to 20 megawatts per minute for safety reasons. But yeah, as we can see, FCRN with the minimum bid, there is very slow ramp speed, and then with the FCRD it's a little bit higher, but it's still within the 20 megawatts per minute. So those are our main markets. And here now the case study. So for the case study, I built a model using an Apros simulation tool, and it's of the upcoming Nujala plant for Fortum. And here is the simplified version. So basically we have the heat accumulator, there is the hot water that goes on the top, and then cold water is at the bottom, and it gets sort of layered. So for the simulation it is just 2 layers, and there's no mixing, but in reality there's also not that much mixing, as it's usually pumped and emptied at a very steady rate. Then we have pipes, and then a pump that is controlled by a PID controller, and its main function is to keep up the pressure difference on either side of the pump, and technically on different sides of the control valve. Then it goes to the electric boiler, heats up through the heat exchanger, and then there's a control valve that it changes the flow in the system. And these are the main components that we are looking, and here is the broader model actually used. So it has just more valves for accurate pressure loss, and then we can see the control systems here, checking the pressure, keeping up that, and then the control valve gets from the PI controller gets the value of the cold water, and then it calculates what should be the flow with the desired power level from the electric boiler. So first you input the power level, and then it calculates what is the required flow rate. And the focus is pretty simple. We want to see how fast the system can react to changes in power. We know the electric boiler can do up to 20 megawatts per minute, but what happens with the temperatures and pressures, and can we get the valve working in unison with the electric boiler so that we can get stability in the temperature, and also we just basically need the flow to match the power output. And then some parameters for the simulation. So there was a power limiter implemented, which takes the target temperature and then the temperature measurement before the boiler, and then also the flow before the boiler, and then it calculates what is the maximum power you can output so that the water doesn't go over 98 degrees. So it just works. We can see here from without the limiter, it is very fast. In working, we see the red one is target power, so when target power is set down in this example, the measured power comes a little bit later because it's controlled by the PI controller. And then here we can see the temperature change. The red one is right after the electric boiler, which is much higher. You can see it goes up to 112 Celsius, which is too much. But then the green one, we can see when it enters the heat accumulator, which is the more important one, as you don't want it to go over 100 degrees, because then there is problems with boiling and steam, and it just shuts down if it goes over that. So that is the more important one, but it's also important to see that if there's a lot of large deviation, it will eventually cause problems. And here we can see with the limiter, it's sort of the same, a little bit slower to reach measured power to reach the target power, but then the change is that the temperature stays at like 98 degrees at maximum, close to 99, but doesn't go like over 100 or close to that. And then also after the boiler, it's only 107 degrees in this case, so it is more acceptable. And then the control valve has a drive time of 180 seconds, which is slower than the ramp rate of the boiler. So it's 180 seconds from 0 to 100% open. And then there was the basic outlook, what the PID controller looks like. In this case, it's just a PI controller, but we can see here how it works. So on the red we have the controller output, and then the green is valve position. So the valve is slower than the controller is going to be, and then because the controller had to be quite fast in this case, it overshoots a little, but then it meets with the valve position, and it doesn't create too much overshoot or undershoot in this system. And yeah, the electric boiler is limited to 20 megawatts per minute. And then now to the tests. So these are tests you have to get through to be accepted into the reserves market. And here we can see, here's the sine wave test basics. So you have 10-second wave speed, 25, 90 and 300, and just means how often it completes one loop. And then you have the megawatt amounts of 1, 3, 5, 10 and 20. And first I just calculated which go into the 20 megawatts per minute, so the boiler restriction. And we saw that at the 10-second test, even 1 megawatt is too much. And then from 25 we can do some. And then in the sine wave actual simulations, I chose the highest megawatt amount for each of the acceptable like tests. So I took the 1 megawatt for 25 seconds, and 90 seconds 5 megawatt, and 20 megawatt 300 seconds. And for the FCRN, the step test looks like this. So it goes down, up, and then back to baseline, and then it has to be within the acceptable margins in the test. And then for the FCRD, we have sort of same, but it's much faster and bigger deviations. So here are the results of the sound wave test. What we can see again on red is the temperature after the electric boiler, and on the green is when it reaches the heat accumulator. So we can see that the 25-second sound wave, there is basically no difference in the temperature at the heat storage. Pretty much the same for the 90-second 5 megawatt test, but then at the 300-second 20 megawatt test we can see that there's a somewhat large deviation both in next to the boiler and then also at the heat storage. But we can see that here it's 98.6 degrees is the highest at the heat accumulator, so it is within acceptable limits. And here are the step tests for FCRN. So first we have the measured power in blue, and red is the target power, and then below it it's the same test, but just the temperature, red after electric boiler and the green at the heat storage. So from these we can see that each one of them is within acceptable limits. The measured power reaches the target power quickly enough, and there is some overshoot in the higher ones, which comes from the controller having to be really fast, so it will try to really fast increase it and it goes a little bit over, but there's a 20% overshoot you can do and 5% undershoot, so the overshoot is preferable. And here the only one is the 20 megawatt. The temperature goes to 102, 103 degrees at the accumulator, so it is not within the acceptable limits, but the other ones are. But then for FCRD, I only inspected the 1 megawatt and 3 megawatt tests, as the other ones were already too fast just by calculating the speeds. And here we can see that here the power doesn't even reach the bottom at many points, and same for when going upwards. So this was not within the acceptable limits. There was too much undershoot, especially in the fast sections of this test. So it would not have been okay. But this is partly because of how the controller is tuned. So it is possible to get it to work with this system if you just adjust it to a smaller bit size, but then it couldn't do the bigger bit sizes. So the results are that the electric boilers are best suited for FCRN, and there are some challenges with the FCRD, but it is possible with specific controller configurations that could be made just looking at trying to get into specific FCRD markets with, for example, 3 megawatt bid. It is definitely possible. And then FFR seems somewhat impossible due to the how fast the ramp rate should be. And then the big problem being the temperature, and in this case the heat accumulator cannot take over 100 degree water, and that was the limiting factor in all the many of the failed tests. What are the economic results? So here we can see for FCRN the average price throughout the years. So it's been like 20 euros and then 14, and then it has gone all the way up to like 40 euros per megawatt. which is a lot of money for participating, but there's also right now average procurement has been around 59 megawatts and average offering 120, so double the offering from the procurement. But as the markets grow, there's gonna be a lot more offerings, and it will eat the average price. As we can see, for example, 2021, 130 megawatts offered and 30 average procurement, and then the prices instantly dropped. But here is also a quick calculation with threshold prices. So if you look at how many bids over 100 would have gone through, you can see that in 2024 you would have made 91,000 euros just from offering every day with €100 price. And then for like example the €20 price, you could have made up to 316,000 per megawatt if you could offer that to FCRN for the whole year. So there is a lot of money in here, because as we saw, 20 megawatts could be possible, 10 definitely could be possible, so that could amount to 3.16 million a year extra revenue. And the challenges and the bottlenecks, obviously the valve actuation speed limits, but here you can see as the valve is not entirely linear, we can see that at first it opens much more for each megawatt increase, but for example if you are running it at 5 megawatts and want to get it to 10, then the ramp speed is 23.8 megawatts per minute. It's the correlating. This doesn't account for the controller's slowness, but just if the valve would move linearly. And then from 45 to 50 degrees it has to open much less, so then it correlates to 47.6 megawatt ramp. So the valve might not actually be the problem. There are also obviously faster valves that could be used, so it is one important part to think about. And then main problem being the temperature control during rapid ramping, and this comes down to how the controllers work and how it would work together with the electric boiler. And it could increase the automation complexity and costs. And there is potential to increase the electric boiler ramp speed. This was just set from earlier designs from earlier electric boiler plants. And the future outlook is that many of the reserves are growing. There are a lot more opportunities and more flexibilities needed in the electricity grid. And it's also for FCRN, the future looks okay for now, as we can see what is the situation in Sweden, where the FCRD prices have gone down dramatically. They have basically flatlined to around €5 due to a lot of electric batteries entering the market, and this will most likely happen in the same way in Finland, but still in Sweden the FCRN prices are quite high, and it looks good for current investments. And conclusions: electric boilers definitely can stabilize the grid, and it is a very good fit for the FCRN markets at around 10 megawatts and above if configured correctly. And then this would drastically bring down the district heating production prices, which could increase increase the expansion of district heating and also get us more CO2 free energy production, in this case heat production. And future research, there's a need for a model that is also connected to the district heating network. Right now it was only the electric boiler and then the accumulator, but you could add the district heating network into it, and you can also make configurations where you run it through the accumulator into the grid, where it works as a balancing like tank in the middle. So it is definitely possible to run it to the district heating network through the accumulator, just having to keep it under 100. And obviously there is possibilities of higher pressure tanks that could work above that temperature, and then full economic models over multiple years should be studied in how realistic is it to offer it, and when you could offer it into the markets, as it has to be running because the FCRN is symmetrical, so it has to have space to go up and below. Thank you very much. This was my presentation. Next, if you have any questions, feel free to ask them.